Hello and welcome back to another episode of Math with Son. Today we're going to be doing an AP Physics 2 FRQ with a magnetism / electrostatics with a capacitor here going on. So we have a radioactive source. It's shooting a positive charge into a magnetic field, and we have a velocity selector. So apparently we're able to change the velocity, and it asks us right away to derive an expression for V is equal to E divided by B1 for the speed of the particle that moves in a straight line through region 1. So if it's going to move in a straight line through region 1, that must mean that the force magnetic must be equal to the force electric. Okay? So we would have to look at our formula sheets to figure out that the force magnetic is equal to QVB. And we would have to look at our formula sheets to know that our force electric is equal to E times Q, or at least that's one version of the force electric. Okay? It wants us to do velocity. It says derive that velocity is E divided by B1. I guess we should put a B1 here because it had a notation. The charge is going to cancel. Okay? Velocity will in fact equal E divided by B1. We just divide. And that to me seems like a one-pointer if I've ever seen one, because we got our answer right away. Check. Part A done. Some particles are emitted from the source at speeds greater than that. So now, if the speeds are greater, which of the following describes the initial path of these particles immediately after entering region 1? And the reason they have to say immediately after is because we have conflicting fields here. We have a magnetic and we have an electric field. If it was just a magnetic, it would be purely circular. If it's magnetic and electric, it's circular for a blip, and then it gets funky because they're very, very different forces going on in different directions. So let's see what's going on here. We still have QVB would equal E times Q. Okay? What did they say we did? We decided to the path. The speeds are greater. So if we've increased the velocity, that means that we've increased the force magnetic, which means force magnetic is going to be greater than force electric. If force magnetic is greater than force electric, that means that we will need to follow the circular-ish path that the magnetic would do if the electric wasn't there. So we put our thumb in the direction of the proton or positive charge. We put our field, it would need to be coming up towards us. So let's see if I can do this while also not curling my hand too much. Thumb this way. Fingers that way, but if we go all the way up, which way is my palm going to face? If my fingers are facing me and my thumb is going that way, my palm would be facing down. So that means that the force magnetic is down, and this would at first follow a circular path downward. So it will curve toward the bottom of the page. Click. Now I did notice on the AP mark scheme that they did some things here that was kind of unique that I don't see very often, but it is a smart habit. Sum of all forces needs to equal 0. The force magnetic plus the force electric needs to equal 0, or minus the force electric needs to equal 0, and they actually had a point for that, which was kind of odd. All right. Explain your reasoning. Well, explaining our reasoning, I'm going to show you exactly what's going on here. So that we don't miss it. So it says the electric force is equal to force electric is E times Q directed upward, the same for all speeds in this particle. However, the magnetic force is directed downward, and increasing that speed would mean that the particle is greater than the force magnetic is greater than the force electric. The resultant force on the particle as it enters the region would be towards the bottom of the page due to, they don't say the right-hand rule. It's interesting. Okay, moving on. Explain our reasoning, done. I like showing you the AP mark scheme for that sometimes. Okay, it says, for all parts from here on out, we are having a constant magnetic field B2 directed into the page is now added to the region. So here is B2 added into the region. Let's see if I can put both of these on the screen. Not easily. There we go. All right. The particle leaves the radioactive source and travels through region 1 in a straight line. So we're going in a straight line through here. And then it's going to enter the magnetic field. So this is essentially a mass spectrometer where we are going to get some sort of radius going on here. This is a field going in the opposite direction, so this is going to end up curling up in a circular path. Because it curled down before with the dots, now our field is going to be away from us, so our palm would be up on the page. And we are allowed E1, we're allowed B1, we're allowed B2, and Q as the only variables. That's going to be annoying to deal with, okay? So we're going to be able to enter this field, and it wants to know, determine an expression for the initial magnetic force on particle 2 in region 2 and state its direction. We've already stated its direction. Its direction is going to be up in a circular path, okay? So the force magnetic will be in the positive y direction originally, okay? And then it is going to change and be inward. So it's up here, it's going to be inward the entire time, and it will be constant. Okay, force magnetic will be inward and constant. Okay, and an expression, well, force magnetic is equal to QVB2. Are we allowed V, though? No. So that's the annoying part. We're allowed E1, B2, B1, and Q. We're not allowed V. So let's see if we can figure out an expression for V. Well, we're allowed E. We're allowed E. So let's see. I'm going to try and figure out a way. I'm just going to write E1, B1, B2, and Q here. That way we have room. So force electric was equal to E1 times Q, which was also equal to QVB. Just so we know, okay? So that would be equal to QVB1, not B2. So we want to figure out QVB2. Well, we could solve for V here. We would get E1 times Q divide by QB1 would equal velocity through here. And the velocity through here will be the velocity that enters B2 with. So we now know our V. The Q's are going to cancel. Our answer was originally force magnetic was equal to QVB2. Well, now I know my V is E1 divided by B1. So there would be our force magnetic equation. And I would clean it up a little bit. I would say Q E1 B2 over B1 is equal to my force magnetic. Done. Okay? So a little bit annoying because we're not allowed V. Describe the changes, if any, the magnitude and direction of the magnetic force as the particle moves in region 2. Well, the magnitude is going to stay the same. Mostly because the speed stays constant. The velocity changes direction, but it is a constant speed. So the velocity changes direction, so a lot of people say the velocity stays constant, but that's technically improper. As it moves through region 2, the direction of the magnetic force will always be inward, and it will start going up, and it will end when it leaves the field probably going to the left. So it's always going to be inward. I wonder what AP worded that as. I gotta find it. Oh my gosh. The force is constant for including a description of the direction changes. So force magnetic does not change. It is always constant. The angle between the velocity and the magnetic force remains constant, perpendicular 90. I probably wouldn't have worded it that way. But as the particle curves, the direction of the velocity changes, and the direction of the magnetic force also changes because it remains perpendicular to the velocity vector. So you would need to say that the force magnetic is always perpendicular to the velocity. Okay. Describe the path in region 2. Well, the path in region 2 would be circular and up. Okay, it's circular and up towards top of the page. We've kind of already answered that. Derive an expression for the charge to mass ratio of the particle. Specifically note any quantities not defined previously. That part bothered me a lot. I'll tell you why in a second. Okay? So, we have a few formulas that we could do. We could say that force magnetic is equal to QVB2. We have already said that. And we need to incorporate a mass. The only way we're going to incorporate a mass is set this equal to the circular mv squared over r, because that's the only formula that we have that we can have an m in. All right? One of the velocities cancels. Bing, bang. So QB2 is equal to mv over r. We got to figure out charge to mass, so I'm going to need to divide by m. Q divided by m would equal v over b2r, also divided by b2. So the charge to mass ratio is equal to v b2r, and we're not allowed v. We're not allowed v, but we've already figured out what v was. Remember from the previous bit? We already figured out that v was E1 divided by B1. So I'm going to replace v with E1 divided by B1 over B2R, which cleans up to E1 over B1 B2R. And when I was doing this problem, I was perplexed. I'm like, how am I going to get rid of the R? I could not figure out how to get rid of the R. And apparently AP is fine with that, and I've never seen this before on an AP mark scheme, but it even asked us to there. It says specifically note any quantities not previously defined. We have not previously defined R. R was not defined, but R is constant. R is constant. All right, I've never seen that. Normally, if you use a variable that's not allowed, you don't get points for the entire thing. But on the mark scheme, it says this. It says E divided by B1, B2, R, and 1 point for stating R is previously an undefined quantity, and the radius is a circular arc with the particle moves in the magnetic field B2. I've never seen that before. But AP's allowed a freebie every once in a while. They do really good stuff. So that's going to do it for this one. Until next time, stay positive, and I will see y'all later. Bye.